So that would give a sense whether these reconstructed components are actually picking up the oscillations or not in an average sense.
Okay.
Do you
So
get that?
area average anomalies. At present, actually, we are not using the anomaly because last time we have seen that although making and normalize our data, the results were not changing. So at present, we are using the original data with just daily values of the rainfall subtracted by the daily climatology.
Yeah, that's the anomaly, right? You
Yeah,
subtracted the climatology, so that's
daily climatology, correct.
yeah,
Yeah.
that's an anomaly, right? So you can just plot the anomaly and that's just the reconstructed component, just to see whether these reconstructed components using modes 3 and 4 are actually picking up some oscillation or not, and those values are actually within the range of these anomalies. That's just to check whether this is actually doing it correct.
So area
Right.
average rainfall, that should be in the time period of the data we selected. Like we selected.
Yeah. I mean, just before the MSSA, whatever you have fed into MSSA, that's just that plot, and that's just a time series. And then on top of that, this RC34.
On top of that, like the time series values of these.
Yeah, just the time series. You can do it over a particular grid point, or just do an area average, just to see whether this is actually picking up the oscillation or not. I mean, to me, this phase composite doesn't. I'm not seeing any propagation characteristic. I don't know whether it is because of the color scheme. Maybe if you use a different color scheme, or so you can see some propagation. But just want to see whether you're really picking up some oscillation.
Right. What would you like be expecting to see if it was
I don't know. I mean, if I'm not an expert in Australian monsoon, but I would expect what I would expect a southward propagation of these bands. Maybe in the multi-year average, you would see some of these propagations, but for this particular year, I am not sure what the
Because it
propagation.
is not repeating the blue color at the phase end 8, right?
Uh,
I mean, it is
yeah.
not uh, in a cyclic manner.
Yeah, phase 1 through 4, they are positive in the eastern part of Australia, Northern Australia, and then there is the sign swaps. So definitely there is some oscillation present, but I just want to see whether it is really
Is
right?
is it one more thing like our day 1 and day 2 are showing significant numbers in all the data rather than day 3 and the day 4, because this year is showing day 3 and the day 4.
The mode 3 and 4.
Yeah, sorry, mod 3 and 4, the significant one for this year, but the next year it will change.
Yeah, it will change. It will change. I mean, that's because, I mean, not every year the ISO will have different characteristics. I mean, for some years it may have a very strong characteristics. The ISO modes will be having much more eigen values. The values will be more than some other
Okay.
years.
So
So that's normal.
my
Yeah.
question is like these two, if you see 1 to 4 and 5 to 8, it looks like one is trough, one is crust,
Mm.
but the oscillation period might be, next cycle might be lying ahead.
What do you mean next
Like
cycle?
if we increase, let us say it is 24 days, 3 and 4, rather than getting 3 and 4 more, we can get 1 and 2, and that oscillation cycle can be visible in these 8 phases there.
No, in basically in phase composite, you are just ignoring its periodicity. You are just dividing it into different phases according to their oscillatory uh, behavior.
So it's a cycle like
So
crust and
even if it is 24 days, even if it is
okay.
48 days, it doesn't matter. When you just do a phase composite, it basically average out all those days which belong to a particular phase. So the time sense is gone in those phase composites.
Oh, this
Right.
phase one means let us say we have 0 to 360 days of the cycle. and the phase 1 is, let us say, 24 days here, so that will add the 24th days phase from that cycle, and
Yeah,
all,
not, I
all
mean, this, so when you say 24 days, I mean, let's say you have 196 days for your total year, right? And
okay.
then you did a phase composite. So you're dividing these 196 days into 8 different phases. Now,
Right.
roughly what you get is around 25 days per phase, roughly. So now these 25 days for each phase may not come in one segment. It would come in different segments because it's an oscillation. When you have a trough, you just pick the first part of that oscillation
24
as
days part, yeah.
yeah, and then
And
again
then
when
the
it,
next trough.
yeah, and then again when you have another oscillation going up, then you just
Okay.
pick up those days. So basically, you're just
Okay, I
picking up those
understand.
days which have similar characteristics.
Mm-hmm.
Okay, so. Uh, Before going into the phase composite, I just wanted to look into the anomaly data, the data you fed into MSSA, and just this reconstructed component, what you have done for phase composites. So that would give you an idea whether this method is actually picking up the oscillation.
So
Right.
we can do area averaging here for X variable.
Yeah, just the area, just do the area average. I mean,
Just plot it, John. Write a command, plot. Oh, first the X variable you have in the window, right?
you must have stored the.
Oh, in here, the X
Yeah. Yeah.
variable. Yeah.
Do whos WHOS, and it will show X variable which has 196 by 5392, and then
Right. Yeah.
do mean bracket X
I
comma
think
2
it should do nan mean.
comma 2. There is no nan value here,
Oh, okay.
and semicolon, and store it somewhere. Oh no.
Oh, sorry.
Yeah, you can
Do,
just
let
name
us
it
say,
Let's call
anom.
it.
variable
Anom.
equal to
Sorry, what did you say?
any
You can
variable
say
name
Okay,
equal,
I'll just call it mean.
equal to mean of X comma 2. I know, like, it's fine, like we can store answer, but we just
Yeah.
size
Yeah.
of mn, and then
Yeah.
plot mn.
Yeah. Let's see how it goes.
Where
Where is it?
where is the plot?
Where is the plot?
Uh,
Oh, it
I
is
don't.
plotting in the phase composite itself.
Oh yeah.
Okay, so can you
I
type
think,
figure,
yeah.
figure, figure, enter, and then just plot mn.
Yeah.
Okay.
Yeah. So it gives. Okay. Now you just calculate the. You must have stored the RC somewhere. The reconstructed component
Who's, yeah,
as
RC is there.
where is it? R.
RC.
I think it's RC.
Yes, RC. Okay. So similarly, just plot the
Put hold
RC.
on. Put
Yeah.
hold on,
Hold on.
space on, and then define another variable MC equal to.
Although I think we have MC already
Oh,
defined
okay.
something.
Then define
Yeah.
any other name.
Uh,
M. Yeah.
Yeah.
Okay.
That's
Equal
fine.
to mean of RC, comma 2, exclamation. Okay. Plot
Yeah. Plot.
MNC.
Yeah, that is fine. I mean, you have to standardize all those values before you plot so that you can get a sense of. But what I can
So
see is that the peaks are actually okay.
yeah.
we can standardize,
Yeah.
mm, or we can do it on secondary axis.
You want me to standardize the?
So you were saying,
Standardize, I mean, just MN minus mean of MNC. You can just define another variable
Yeah, that's what I was going to do.
by standard deviation of MNC. That's
Yeah, MN's standard equals.
STD. But you can write this in a single command.
That's true.
Yeah.
So
MN
I guess I
mean
should do MN divided
minus.
by.
So you have to subtract the mean as well.
Yeah. Well, didn't we just take the mean of? Oh yeah, hang on.
Mean of MN and then put everything in one. Yeah.
And squeeze also.
Do you need really this?
I don't. Do we need squeeze?
I don't know. I don't think
Okay.
it squeezes
It may
because
work,
it's
I
just
think.
one vector. Yeah, it should be fine. Yeah. Now you plot.
Should I clear it? Make a new figure, probably.
Yeah.
Otherwise, it won't.
Yeah. Now you plot MN's standard deviation and
Hold on.
Yeah.
Hold on.
yeah.
And then standard deviation. Yeah, that looks better.
Shows. Yeah, it shows some decent oscillations. It's fine.
Yeah.
It's fine.
Right.
And if you normalize the other one as well, it will show the actual
Oscillations.
The time period of these oscillation is around 20.
24 days.
24 days. Yeah.
So let us see, from 120 to 140, it is 20 days, right? So around 24 days. Okay.
Right.
Yeah.
And this is another about 24-day oscillation right here between these two troughs.
Yeah, I mean that 24 days coming out from a Fourier spectra. If you do a Fourier spectra of this
Of the rainfall data.
But but when you saw the phase composite plots, you mentioned like it is not giving the oscillation signature.
Yeah, I mean that's maybe because if you use some other color scheme, I don't know. I mean I don't know how the oscillations are observed in Australian monsoon.
Right.
I'm not sure. Do you have any other previous studies that have shown these kind of oscillations of ISO timescale for Australian monsoon?
I haven't done any phase analysis regarding
I mean,
this.
do you have any other studies? I mean, some other papers that you have read through and that have discussed these propagation characteristics over Australia?
Not that I recall, because I just started looking into this, so
Okay.
I'd have to read a little bit more into that.
So it's just what I can see is you have a very prominent, or the strongest signals are over the northeastern part of
Right.
Australia. And is this the region where you see the mean is maximum?
Yes.
That makes sense. Okay, so in the phase one, it's just positive, and then in phase two, it becomes stronger. And then in phase three, it becomes weaker, and then gradually
Becomes negative.
Yeah. Yeah, I mean, I may not be a very good judge to say that.
Yeah.
Because I have no expertise in Australian monsoon yet.
Yeah, I might need to talk to Vasu about this.
Yeah, but I also you may look into some other papers of. I mean, Harry Hendon might have some good papers on ISO.
On this, right?
Okay. Yeah. Another question is like the second one. So year to year, these 3 and 4 are varying. So when we have like 115,
yeah.
How do we select which mode we have to extract as a phase composite?
Yeah, so for that, what I have done with Indian monsoon is you have to look into the characteristics of all these modes that are becoming significant and oscillatory within this band. For Indian monsoon, we have a very nice categorization, and modes above 20 or 25 days periodicity will have these northward propagating structures that will be a dominant feature in that propagation, and modes with around 10 to 15 days periodicity will have an westward propagation. So
So to see the propagation, do we normally have to plot the lag plots, lead lag plots?
uh, you can see it in the phase composites ideally, and
Can
I
you
mean
show us your paper where you are saying these comments for the Indian monsoon so that we can have some theoretical idea also?
yeah, sure, yeah, I have that somewhere. Okay,
And you can share the screen.
yeah, just 1 second. Yeah, I will just pull up my thesis actually. Yeah, so I can share the screen.
You can end the share,
Okay.
John.
Yeah.
Yeah, can you see?
Yes.
Yeah, so this is with the trim data. So this is the region I used for MSSA. And this is mean JJ's climatology and standard deviation. And then when I did eigenspectrum for 1998, it looked like this. So I didn't get any particular mode with more than 100 years of periodicity. So what I got is some significant modes above 20-day periodicity. These first two modes were around 37 days periodicity. And then there was one around 27 days. And then there was one with around 22 days. And there are few with less than 10 days periodicity.
Right.
So I looked into each of these modes. I mean, when you get a pair of mode, that's definitely going to be an oscillation, and there is no doubt on that. But these single modes are very tricky to deal with. I mean, they may have some oscillatory components, or may not have some oscillatory behavior.
Right.
But still, they have a significant. They are significant. So what I did was I checked with these two modes how the phase composite looks like, and then added these two modes as well. I mean, if it makes any changes or not. What I observed is if you just took these two modes and as well as, I mean, these four modes, that doesn't make any very big difference, but it just
Right.
adds some more details on the structures. So I so 20 days was a kind of a threshold. So I took, if any mode that have any mode that has a periodicity of more than 20 days, I defined that as a low frequency ISO. And if any mode has a less than 20 days periodicity, I defined that as a high frequency ISO. So that is very, I mean, crude way to define low frequency and high frequency ISOs. You need some threshold. You need some threshold to define that. I mean, two different ISOs. So I
Right.
basically took 20 days as a threshold. So once
But
that is
there are
done,
other significant values also, right? You mentioned that those are not falling in between the bars. Are the
yeah, these are also significant, but they are very, very small. They have very small eigenvalues. So they're basically, if you take them or do not take them, they don't actually make any difference. They're actually almost 3 to 4 times less than these values. So if you
okay?
look into the yeah.
Right.
So if
So
the
they're
eigenvalues is less, then we can also like approximately say that they might contribute less.
Yeah. So they have a very small variability. Eigenvalues basically represent the variability or the variance explained in these modes.
Okay.
Yeah. So so this is the RC12 for this 1998. So this is phase 1, phase 2, phase 3, phase 4. So as you can
Yeah, it
see,
is
there's a
showing it is showing the
development of
oscillation.
this negative anomaly over here.
Hmm.
And then in phase 2 it propagates eastward and it gets intensified. Then there is a strong northwest southeast tilted band gets established, and then it propagates northward, further northward, and over the foothills of the Himalayas it dies of it's kind of getting suppressed over there. Now this is for one particular mode
Year.
for one particular mode for one particular year. Now this looks kind of noisy when you do all the modes, all these low frequency ISO modes that has periodicity beyond 20 days, I mean above 20 days. And for this 17 years of data, you get these nice structures.
But this is looks like northward propagation
Yeah, this is northward propagation, right?
rather than eastward.
It has eastward component over the tropics.
Yeah, eastward component it does has.
Yeah. So uh, does it make any sense? I don't know how.
So one more
Yeah.
question, like you mentioned you did for 1998 to 2014. So
Right.
in all years you were getting low frequency ISOs you are saying, right? What about the high frequencies ISOs?
Yeah, for high
So
frequency
to low
ISOs,
frequencies ISO you have defined those which have periodicity less than the 20, correct?
right.
So when you define the periodicity less than 20,
Hmm.
how that script is working, where you need to define the less than 20 and greater than 20.
So that's actually worked for Indian monsoon. I am not sure about Australian monsoon. If 20 days will work or not, you have to
So,
look
but
into
where,
at least.
where
I
we
mean,
need to define it?
in the code you don't have any. There is no such place where you can define the 20-day periodicity. I mean,
So how
uh,
generate, since this particular code generate the phase composite, right?
yeah, so for that I think you what you can do is for the reconstruction in that function, you have to go into that function, and then while you are reconstructing, just pick up those modes with that has a periodicity of more than uh, 20 days. Actually that has I have a different code for that in MATLAB, and I did the reconstruction and this phase compositing in a different uh, function or different MATLAB code while I was plotting. I can
Okay.
share that to you in some time. I mean,
Yeah.
and that would be easier for you to just calculate the.
Yeah. So is it in Pegasus?
No, it's in Wind server.
Okay. Okay. Can you tell me the path? I can just have a look at.
I have to open up myself.
Yeah, we can actually.
Yeah,
I'm in the wind.
I have to log in as well.
I'll be right back.
And
VPN
that's the
connection.
only code. Like if we change that code, we will know that these are the numbers. If low frequency and high frequency, we can change in that. And
Yeah.
so there is no
Once you
code has to be replaced.
uh, that code, I mean, that is not very user friendly, and that is not written as a function. I just use that as just to plot or calculate the phase composite. So you can
I
use that, or
understand.
and you can just grab some part of it.
So where it is actually?
Yeah, just a second. I need to connect it.
Oh, I cannot access your, you need to provide the permission of your folder,
Run it back.
the wind.
Yeah.
The one thing I was thinking, so your the figure here that you're showing clearly shows the propagation, but your domain is so much larger than the domain I used.
Right, right. That could be one difference. I mean, one thing you can do is if I show you these kind of lat-long diagrams or let's see, these kind of diagrams. I mean, Haug-Muller diagrams or
Haug-Muller diagrams, correct. I was
You're
saying.
right.
you can look into that, and that may give some information.
Some insight, right?
So this is for June to September. You can do it either that way, or you can just plot like this. I mean, based on the phases.
Right.
So these are basically 8 phases, and if you just plot along some particular latitude or longitude band against time, that may
Right.
give some sense of propagation. Okay, let me go through wind and okay.
Also change the permission in the wind, okay? For the NIRPOM folder.
Yeah, I will do that. Just
And is it possible to increase the domain, John?
Not with the data set I have.
So this is the data, like Australia is very short, like you can.
Yeah, it's not a huge. I
I
mean,
think Vasu provided you the data for the full Australia, correct? Complete Australia.
yes,
So
but unfortunately, beyond, if I go any further south, you get to the arid central regions, and there's just no rain there, so you're just not going to see any signal at all.
okay.
yeah, the mean is actually that's actually may not be a good idea to include further south, because that may not include the monsoon domain over
Yeah,
Australia.
exactly.
Okay.
Yeah, so I've shared I'm sharing the screen
Yeah.
Right.
where I have used the IMD data for, this is for IMD data, not the trim one. I just found
Okay.
this one. So I will just go through step by step. So this is, as you can see, I mean, I'm adding path here and then start year, end year.
Right.
And then I'm reading each year separately and then storing it in P variable, right?
Right.
Okay, and then this is just creating the size of P, and this step is creating the anomaly. So P anom is basically the anomaly calculation.
So this is P means the rainfall, right? IMD rainfall.
Right, yeah. It's IMD rainfall, India Met Department rainfall.
And then you have computed the anomaly. Okay.
Yes, this P anom is anomaly. Now, this next step, moving mean, I must have included this moving mean in the MSSA folder. So there will be a moving mean function in the, over there. So you just apply that with a 5-day moving mean. So that basically removes all the very high frequency and noisy data from the noise from the data. So
Okay.
I think you may not have incorporated this step. This step is important if you're using rainfall as your variable. If you're using stream function or let's say OLR, those are pretty smooth data than compared to rainfall. So if you're using rainfall, it is highly recommended if you use this moving mean just to smooth out the signal and remove the very high frequency noise.
Right.
Now at this step, what I'm doing is creating that latlon data into the space data, right? So you did those part using a Fortran code, I think.
Yes.
So that's basically done here.
Yeah.
Okay, so that's removing the 4-dimensional number of, so 4D data means num years, the total number of years, dy is day, nlat is the number of latitudes, and mlon is longitude. So that's basically, it's reshaping the data into 4D into 3D. So
right, which is
this
basically
time,
turning it into time by space.
right, and then you're in this step, I'm removing the annual mean. So that's centered data.
Right.
So I didn't normalize. It was not necessary to normalize the data for this because I already removed the anomaly.
Okay.
And then in this part, I'm removing the missing values because IMD data had some missing values. The NaN values were very particular domain. So you just have a land data over there.
Right.
Now, how I did that was creating this P1 file. This P1 is somewhere in, I must have stored somewhere. Yeah, so this is P1.
Right.
So number of years, days.
P1 is number of years, days. Yeah. What happened? It's not going.
Yeah, it's been a little slow this morning.
Yeah. No, I think it will work. Oops. Yeah. Yeah. So once you have the missing values removed, so this is just basically a 2 for loops and 1 if loop. If you have a NaN value over for a particular, I mean, for that mask file, then you just put NaN value for all those files as well, and then remove those NaN values from your data.
Right.
So this is how you define the matrix. So NNZ is number of non-zero values with not ISNAN, and then so on and so forth. You can just look into
Right.
that. So once you have that, then you perform the MSSA.
Okay.
So I have numpc as 30, m is equal to 60, ns equal to 1000, method is equal to reds, and I did not rotated the EOFs. So that was
Right.
very necessary step to do at this point. And then I RCY, RC1, these are two variables that I have defined for storing the data. And then this is basically this one.
You are not using the subroutine function. You are just including in the Fortran, MATLAB code itself.
Yeah. I mean, this is just a MATLAB code, and then I'm applying MCMSS this function.
Oh, this is the function.
Just like you did, that function.
Right.
Okay. Mm-hmm.
And then you calculated this EF, V, AF, FE, and all these variables.
Right.
These are all in the MC structure.
Okay. Right. So it seems like we've done basically the same thing, just
exactly.
using Fortran.
Yeah. Now these steps are basically I'm sorting out the frequencies, and then you can just go run through this code, and then you can understand what I have done here. So that would be easier instead of I am saying what I have done. And then what I have done is I'm taking all those frequencies that is more than 10 days periodicity and less than 20 days periodicity. So if that condition is fulfilled, then I'm taking all those indices and then I'm storing it on I1.
Okay.
And yeah, okay. So that once that I1, I have to basically, if you run MRC, the reconstruction, how to calculate the reconstruction, you have to give the
Right.
indices, right? So AF, EF, NumPC, and the indices. So basically, I1 are the indices for those modes that is a periodicity between 10 to 20 days.
Right.
So that's for that I needed to calculate I1, and for that I1 I needed these steps.
Right.
Once
Okay.
R sum is you got the R sum, you just calculate the recon grid, and then it follows.
Right. Okay.
And yeah, and then just to put that into the same grid as in the lathlon, this is basically you're putting it in the lathlon grids again in just a for loop,
Reconstruction. Okay.
and then and then just write the data.
Yeah. So you basically just told the MATLAB code, hey, look for in that, like when it outputs the modes with the periodicity, you just said look for periods between 10 and 20,
Right.
and then tell me what the index is,
Can
and
you
then
show me? Yeah, you go ahead. Sorry.
and then from there you basically just ran the MRC, the reconstruction with the those indexes that it just pulled out.
Exactly. Yeah, that's what is done here.
Okay.
Yeah. So can you show me, Nirupam, just above when you define? Say 1 by frequency where you have defined and you are comparing 10 days to. Okay.
Yeah, this is Fj is equal to 1 by frequency. So that gives the periodicity.
So when we get the output in the print, so which one is, so fs is the, like, where is the, which variable is for the mode?
I'm sorry.
The mode is I.
The mode index is I.
Yeah.
So this is not the MSSA code. I mean, the MSSA folder that is a different. I am using those codes in that folder.
Mhm.
MSSA MC and then MRC recon grid, and then I have not done phase compositing here. This is not phase compositing.
Yeah, this is just simply trying to pull out the phase composite
Right.
data. Yeah.
So
you are
this
saying,
is,
just I want to understand more about that, like that loop. So you are saying like fj is greater than 10, and then fj less than 20. So either it is. So what does it mean? Either, so it is a mode 10 to 20 days.
Yeah, so this is the
I mean,
high frequency.
Yeah, it's just the high frequency. You can change it to, I mean, let's say 20 to 60, 70. I took 20 to 60 for the low frequency.
Like for what we had just done with our 1900 data, like if we changed it to 20 to 60, so then our 24 mode would come out, like our 24-day frequency mode would come out.
Right.
So then it would save, if I'm getting this right, it would basically save into the variable I1, it would save 3 and 4.
Yeah.
And then, so then it would come down, and then we ran our sum. It would just do 3 and 4.
Modes will come in I1 in this case?
I mean,
it depends on the year.
It depends upon the year. If for your case, I mean, if you took 10 to 20, and then you might have modes 5 and 6 with a periodicity of around 12 days. So you get two modes for this year.
So if it is coming 1, it will just come as a 1 mode, right?
Yeah, it will come as a 1.
And then it will be summed, and you are constructing the RCs. Okay.
Right. Yeah.
So this Amit is, I think, the like when we were trying to figure out how to automate our code so that it could just basically pull out right away the modes that we need. This is what we were looking for.
Yes, and then we have to define the threshold value which he mentioned, like greater than 10.
Yeah.
20.
Yeah, this is the threshold. This line is the threshold, basically.
Yeah. And based on that, it will just R sum, like the construction has been completed based on the mode summation, right?
Yeah.
Yeah. Yeah. The total number of modes. I mean, if you have 2 modes, then it will just add R5 plus R6, and then RC5, 6.
So this you have done in all MATLAB code. I think that will be a good way further.
Yeah, I think that was the question that we were having earlier, is how to do that, and I think that's the answer that we were looking for.
Yeah. So
Okay,
Nirupam,
so
will it be possible
I
to
will share this
share this
code
code
to
also?
you. Yeah, I will share this code to you. I'll send by email.
Yeah, sure. Thank you.
Okay.
So now can you go to the paper?
Yeah. Okay. Yeah.
So yeah, in this case, we are using data from 1st April to 30th of November, correct?
Uh, for which one?
For,
This one is trim
yeah,
data. I mean, for this one I use from May to October.
May to October. Can you
Yeah.
go up with the that frequency figure?
Uh, which one?
Uh,
Yeah.
the frequency, the modes. Sorry,
This one.
above it, the first figure, I guess. Yeah, this one. This one. So this is the basically threshold you define for the low frequency and high frequency.
Yeah,
Yeah,
20 days is kind of okay. I mean,
that I've seen is kind of the standard. I've read a few papers about that as well.
yeah, you can define it as 30 days or 25 days. I mean, the result should not change vastly. I mean,
That
it
How
should
much,
can you
yeah.
remain
define it
consistent.
for Australia? Like these type of modes are not very clear in Australian monsoon.
Yeah, that's why I said. I mean, I have not much expertise on Australian monsoon. I have to go through some papers.
And then once,
What kind
okay,
of?
we will go that. So let us say, assume that somehow we are able to define the threshold. Then we should get these below second next figure composite structure. Like there should be some propagation or oscillation that we could see, right?
Yeah, I mean that I should say. I mean, for Indian monsoon, northern propagation was very easy to trace,
Hmm.
but the high frequency oscillations may be very noisy to and with the rainfall data, particularly with rainfall data. If
Hmm.
you are using stream function, that would you would get very nice westward propagations from the East Pacific region towards the West Pacific region towards the Indian region. But with rainfall, it is very difficult to trace the westward propagation in rainfall over India. I will show you some figures. Yeah, so this is basically the westward propagation for high frequency ISOs. And it again shows some tilted structure over India. But again, if I plot some Hofmolar diagrams or Latlon diagrams, it shows a westward propagation as well. I will show you one figure. Yeah, so if you see this uh, diagram C, so this is basically a curvilinear phase diagram. So I took some
Right.
grid points over this region and then plotted these locations as y-axis against the phases. And that showed a very clear tilted structure. I mean, that's a propagation
Right.
along these
Westward,
lines.
yeah.
So that's basically northwestward propagation along these locations. So
Right.
that shows a northwestern propagation. Now, this is very difficult to identify because rainfall is a very noisy data.
Yes.
But again, I have done MSSA with stream functions as well for this domain, and I got very nice structures of western propagation. So those are
Yeah, this figure is actually
things.
not figure because John has to identify the correct location.
Yeah,
To
yeah.
get
I
the,
think the best way to do is just to look into the Hofmolar type diagrams.
Okay.
Okay.
Right.
okay.
And maybe I'll also look into some papers on the ISO over the Australian monsoon, and then we can define some threshold, which kind of threshold we can define for high frequency and low frequency ISOs. And do we really have a prominent high frequency ISO?
Sure. So what we can do at present, rather than like we have created a Fortran code, MATLAB code, and
high
then
frequency isomer.
the Fortran code. What do you say? Just we read our binary data, but it is too much because Fortran code can be run faster than the MATLAB code. That is the one advantage we have. Uh,
It's freeze.
Sorry, come again a bit. We lost you
oh,
for a minute.
I was saying like
Yeah.
Nirupam prepared a single code like simple MATLAB, like everything is completed in the MATLAB. And the similar task we
Yeah.
have done. First, we have configured our rainfall data. I mean, we rearrange our rainfall data using Fortran code, and then we prepared a MATLAB code to compute these phase composites. And then we again prepared a Fortran code.
Right.
So the
No,
benefit
it
of
is very difficult to go back and forth. I mean, it is
yeah,
always good to use some single code to just calculate all the things. And then when you plot, I just took the created the or written the NC file, what I have to just plot. And then once you have
but
the NC
for
file with the reconstructed
yeah,
components, the phase compositing is also not difficult.
yeah.
And then just plot to
Like
plot.
it is like his data, it's a huge data. For Indian region, there are only 135 to 129 grid points, but in his case, it
Yeah,
is 601 by 201. And I
yeah, yeah.
don't think so. Like MATLAB can handle that one if you don't have the good brand.
Yeah.
Yeah, that's a problem with MATLAB. I mean,
So, so in that sense, it's quite good. Like we have first rearrange our data itself, and then we just
yeah.
use a single file, and then we are basically working with the photon code.
But
But your code
if
is
you're
good.
looking into large scale structures, do you need some this high resolution data for your analysis? You can just interpolate the data into and reduce the dimension size.
Yeah, that's true. That's true.
Yeah.
Yeah, you can discuss with
There's a
Vasu
one more
and
question
then
I have. Like, let us say rather than doing MSSA in time, if we do MSSA in space, are we gonna get the similar structure, similar figures?
what do you mean MSSA by space? That would be a very different thing to start with.
Like, okay, is there any paper which has done that MSSA with space?
I don't know. I'm not sure about that.
Okay.
MSSA with space. I mean, it would. What would that mean? I'm sorry, I cannot answer that. I have to think what
Yeah.
that means actually.
Okay. It's a random question just came to my mind because we can flip the space to time and then we can just reconstruct the components. But
Hmm.
when everything is being described in terms of the space,
Hmm.
okay, well, like it might be a random question.
Yeah.
So, do you have any other queries, John?
Not at the moment. I think
So,
I need to discuss a few of these things with Vasu.
yeah, because we have to get a stable mode
I
first.
think, yeah, John, you can send these time series plots for one particular year and one phase composite diagram to Vasu, and then let's see what if he has some insight on the propagation characteristics. He can
Yeah.
provide.
I mean, we can ask him about these things tomorrow during the group meeting.
Yeah, yeah,
So I'll see what he says tomorrow about that, and then we can kind of go from there.
yeah.
In the
Okay.
meantime, I guess I can just try to see if I can't produce some of these like other figures.
Yeah.
Okay,
Okay.
so let me stop recording.